Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course. States of matter. Today we begin with lecture 9 from the course, but make sure you watch the previous ones before viewing this one. The last lecture we learned how to deal with the problems based on the Boyle's law. So I hope the whole concept that is clear to you. In case you have any doubts, please feel free put them in the comment section. You can email them to us. The email ID is written on the last slide of the lecture. Also, you can join us on the Facebook page of the channel that is by the same name of the channel itself, that is H2O Chemistry. One more advantage you will be having on joining us on the Facebook page of the channel is that we keep on posting the previous year questions on the Facebook page. So that will be helpful for you if you can keep on practicing those questions as well. This gives you a better understanding of the concept. This helps you keep on practicing the previous year examination questions, and we are always there to help you. Now, in this lecture, we will be discussing the second gas law, that is the Charles law, and this, like the Boyle's law, which gave us a relationship between pressure and volume, keeping the two other, the temperature and the number of moles of the gas constant. This law is going to give us a relationship between temperature and volume. So what are we going to keep fixed over here? Well, it is going to be the pressure and the mass of the gas. This law was given by Jacques Charles in the year 1787 and Joseph Gay Lussac in the year 1802. Now, this law, as you can see, is being given by two scientists in a span of about 15 years. And now, the credit for the name of the law is only after one of the scientists, that is the Charles law. Now, why is this so? Well, there is an interesting story behind it, and I would like to actually share that story with you because stories make things interesting, right? So, I hope off and on you would like to hear certain stories which will make your study more interesting. But before that, also in this lecture, we are going to learn one very important thing, and that important thing is going to be the Kelvin scale of temperature. So you've already seen the relationship of the Kelvin scale with the Celsius scale while we were talking about temperature in the lecture on the measurable properties of the gases. But here it is actually from the Charles law that we will be developing and understanding how the Kelvin scale and the Celsius scale, they are interrelated to each other, right? So, as I was telling you that I'm going to start this lecture with the story. So let us understand what is going to be this Charles law actually from the story itself. And the story is of Charles himself. So Charles, he was born on 12th November 1746 in France. He initially, in his early career days, was a clerk in the finance ministry, but then turned to science and experimented a lot with electricity. Well, one thing before I continue further, this story is not important from your examination point of view. So you may be thinking that, well, this I'm telling you because you are supposed to learn it. Well, you're not supposed to learn it. I just want you to enjoy the story. Okay. So just sit back. You do not have to write anything. Just listen to the story before we continue further with the lecture. So Jacques Charles, as I was telling you, that he turned into science. To be a science student and then experimented a lot with electricity. But I am not again going to focus on his other achievements in science. Here I'm going to talk about one very interesting, specific achievement of his. And that achievement of his is that he was one of the two riders of the first manned hot air balloon in 1783. So these days, hot air balloons, they are considered to be an adventure sport, right? So people do enjoy taking a ride in a hot air balloon, getting their selfies clicked and so on. But it was this Charles, who was the first rider of the hot air balloon, with one other person whom he got associated with, who was developing the balloon himself. So the person was Robert. So Robert and Charles, they were the first two riders of the hot air balloon. They had their initial problems, but eventually they succeeded in getting a ride in a basket which they had attached to the balloon filled with air, which they heated by burning straw. Their ride, yes, they had a ride. This lasted for 20 minutes over Paris, and this event was being witnessed by King Louis of France himself. So this was a special event, a very important too, because this was first time that actually man had flown, and this seeded into the minds of many others a thirst to fly. So nowadays it is considered so simple that we have to sit in a plane and we travel from one place to another. But the journey into the air of mankind, this began with the ride on this hot air balloon by Charles. So I hope you can understand how important this ride is today for us. So now this was not at all a joyride for Charles. He deduced that on heating the air had expanded inside the balloon, made it lighter than air, sorry, outside, and this had caused the balloon to rise with them as the riders. So he began studying the changes of volume of the balloon which were taking place by taking different gases, and by 1787 he developed a very important understanding which we today know as the Charles law. But still, I have not mentioned anywhere about Gay-Lussac. So where does he come in the picture? Well, actually, Charles never got his work published. It was Joseph Gay-Lussac who made definite measurements and published his results. But he credited the discovery to the unpublished work of Charles, and hence the law got the name Charles law. So with this story in mind, let us learn what is the Charles law. So the Charles law states that for a fixed mass of a gas at constant pressure, volume of a gas, this increases on increasing temperature and decreases on cooling. And this is very easy for you people to understand now, because we've done in detail the discussion on thermal energy and the intermolecular forces. So what we have learned is that when we are going to increase the temperature, the thermal energy of the gaseous molecules, that is going to increase. With that is going to increase the kinetic energy and the speed of the gaseous molecules. And when the thermal energy is going to increase because of the increase in temperature, you can also understand that the intermolecular forces, they are already quite weak in the gases, and with increase in the thermal energy, which is going to be now much more than the intermolecular forces, the molecules, they are going to be free to move away from each other, away from the intermolecular forces of attraction, right? So what is going to happen when the gas molecules, they are going to move away from each other? Well, the gas is going to expand, and when the gas is expanding, what is happening? Well, the volume of the gas is increasing. So what do we understand? We understand that when we are going to increase the temperature, the volume of a gas is going to increase. And this is what was happening in the hot air balloon also. So the balloon had air into it. The air was heated, the gas expanded, or you can say the air expanded, the balloon that became bigger in size, and also when the gas was expanding, what has happened to the density, right? So the number of molecules per unit volume, that is going to decrease. The density of the gas is going to decrease, and this density becomes less than the air outside, and being less dense, it is going to become lighter, and when it will become lighter, the balloon is going to rise up in air, right? So I hope now you can understand and correlate the science of the hot air balloon. Okay, so what we have now learned is that the volume of the gas is going to increase on increase in temperature, and it is obviously going to decrease when we are going to decrease the temperature, that is when we are going to cool a gas. Okay, now what we have taken over here is the fixed mass of gas at constant pressure, because the change in pressure and the change in the amount of the gas is also going to have its effect on the volume, right? So volume and pressure you have already studied in the Boyle's law, that if you are going to increase the pressure, the volume is going to decrease, and if you are going to decrease the pressure, the volume is going to increase. And what we want to study is only the relationship between volume and temperature. So for that we have to have a fixed mass of gas at constant pressure. I think now this is clear enough. Now, the next thing that comes into anybody's mind is going to be that how much volume of a gas is going to increase when we are going to increase the temperature by a certain amount, right? So this is also what Charles' law gave us. This experimented it, they found it that for each degree rise in temperature, the volume of the gas increases by 1 by 273.15 of the original volume of the gas at 0 degrees Celsius. So what this means is that if we have a gas at 0 degrees Celsius, okay, so supposedly the volume is V naught, right? Now I'm going to increase the temperature of the gas and take it to 1 degree Celsius. Okay. Now what is going to be the increase in volume? When the increase in volume is going to be 1 by 273.15. I will just write for simple purpose 273. Okay. So the volume is going to increase by 1 by 273 of V naught. Right? So what is going to be my final volume? My final volume will be V naught plus 1 by 273 of V naught. So this is going to be my volume at 1 degree Celsius, right? Now if I increase the temperature further, I take it to 2 degrees Celsius, okay? So 2 degrees Celsius means that I will be adding up another 1 by 273 of V naught. So 1 by 273 of V naught plus 1 by 273 of V naught is going to be what? It is going to be 2 by 273 of V naught. So what I can write is that V naught plus 2 by 273 of V naught is going to be my volume at 2 degrees Celsius. Right? So similarly, if I now increase the temperature to 3 degrees Celsius, instead of this 2, I will be putting a 3. So now to generalize it, what we can say is that a volume at T degrees Celsius is going to be equal to what? It will be equal to V naught, the initial volume, plus T by 273 into V naught. Right? So I hope this thing is very much clear to you how we get this, what I have put in the square, okay, rectangle actually. So it is V naught plus T by 273 of V naught, which is going to be my final volume at T degrees Celsius, or when I increase the temperature of a gas from 0 degrees Celsius to T degrees Celsius, my volume is going to be V naught plus T by 273 of V naught. Okay, so now if you want to write this down, please do write it, because I'll be rubbing this off. Okay, I am going to just put this equation which I have over here into a printed form now, so that it is clear, because my writing does not come up very clear with this digital pen. Okay, so what do we have over here is that if the volume of the gas at 0 degrees Celsius and T degrees Celsius are V naught and Vt respectively, then Vt is going to be equal to V naught plus T by 273.15 of V naught, right? I hope now you understand how we have got this. So mathematically, we can also write this as Vt equal to V naught plus 1 plus 2 T by 273.15. I have just taken V naught to be common, and also I can write this as V naught into 273.15 plus T over 273.15. Right? Now please be very attentive. What I'm going to do is that I am going to write this equation as Vt equal to V naught into Tt. You can understand this is a capital T, this is a small t divided by T naught. Now what have I done over here? Well, I have written this 273.15 per plus T degree Celsius temperature as another temperature capital T, right? So my temperature in T degrees Celsius, to this I have added 273.15 and I have got another temperature. And this is a new temperature, and actually this is not a new temperature. Well, this is something that you have learned already. Well, this is the temperature on the Kelvin scale, right? So you've already learned then when to the temperature on the Celsius scale we add 273.15, the temperature is going to be the temperature on the Kelvin scale. And similarly, this 273.15, I have written this as T naught. So this is the temperature at 0 degrees Celsius. So what have we done? 273.15 plus T plus, but this T on 0 degrees Celsius is going to be 273.15 plus 0. So this is my temperature on the Kelvin scale, which is corresponding to 0 degrees Celsius. Fine. I hope this is clear to you. And now this is also clear to you that how we have got the relationship of the Kelvin scale and the Celsius scale. On the Kelvin scale, the temperature is going to be equal to 273.15 plus the temperature on the Celsius scale. And this Kelvin temperature scale is also called as the absolute temperature scale, and this is also called as the thermodynamic scale of temperature, and this is used in all scientific works. So I hope this is clear to you people how we have got this equation plus how we have got the relationship of the temperature on the Celsius scale and on the Kelvin scale. So I can just rewrite this equation as Vt over V naught equal to Tt over T naught, where this capital T is denoting the temperature on the absolute scale or the Kelvin scale. And I'm going to just carry this equation further on the next slide. So I hope this is clear to you people. So now the equation we have is Vt by V naught equal to Tt by T naught. And what is this actually? This is the volume at 0 degrees Celsius, or you can say that this is the volume which we started with, right? And this was at temperature in Kelvin scale, which was equal to 0 degrees Celsius. So this is the initial volume, this is the initial temperature, right? And then we started heating it and increase the temperature to T degrees Celsius, which we are now representing in on the Kelvin scale as capital T. Fine. And correspondingly, the volume which was expanded, the final volume we have is Vt. So we can rewrite this equation in the generalized form as V2 by V1 equal to T2 by T1, where V1 is going to be the initial volume, V2 is going to be the final volume, and for this initial volume the temperature is T1 and for the final volume the temperature is T2. I hope this is clear, but just remember this, that this is the temperature on the Kelvin scale and not the temperature on the Celsius scale. You are going to commit a mistake, a big mistake, if you just write down the temperature in the Celsius scale and write this as V2 by V1 equal to T2 by T1. That is going to be wrong. Just remember the volumes are going to be taken on corresponding to the temperature on the absolute or the Kelvin scale. Fine. So now I can just rewrite this equation as V1 by T1 equal to V2 by T2, or I can say that V by T is going to be constant, and this constant we are writing this as K2. So you remember for the Boyle's law we wrote the proportionality constant as K1 so that we can differentiate between the different proportionality constants for the different laws. So V by T, now we are saying this is constant, and the value of K2 We can also write this as V equal to K2 by T, where the value of K2 is now going to be very important. This is going to be determined by the presence of the pressure of the gas, the amount of the gas, and the units in which the volume V is expressed. And this is also very easy for you to understand once you have in mind the ideal gas equation. So in the Boyle's law also, I told you that it is going to be just a sneak preview into the ideal gas equation, because we have not learned that yet, and that we will be learning when we will be combining all the gas laws. So after combining all the gas laws, the equation that we will be getting is going to be PV equal to nRT. But now from this equation, what we are going to see is that what is the value of V coming up to. So V will be equal to nR by P into T, and I want you to compare this over here to the equation number 5, that is V equal to K2 by T. So from here what we get is that K2 is going to be equal to nR by P, where N is going to be the number of moles of the gas, R is going to be the gas constant, and E is going to be the pressure of the gas. Right? So R is a constant. Obviously a constant is not going to matter. It is not going to change the value of K2. What is going to change the value of K2? It is going to be the number of moles of the gas and the pressure of the gas. So the value of K2 will be dependent upon the mass of the gas, the amount of the gas, or the number of moles of the gas, and the pressure of the gas. A very important thing over here, please do remember the relationship of K2 with pressure. With increase in pressure, the value of K2 is going to decrease. And I hope you will understand the significance, because you have seen it in the graphs related to the Boyle's law also, right? So we saw in the Boyle's law that the K1 proportionality constant for the Boyle's law, that was directly proportional to temperature, and here K2, the proportionality constant for the Charles law, is going to be inversely proportional to pressure. So when I'll be discussing the graph on the next slide with you, you will be able to understand the importance of this relation of K2 with pressure also. Right? So now what we can do is that we will be now redefining the Charles law according to the equation number 5 that we have. So what we have is that V is equal to K2 into T, which means that V is going to be directly proportional to T, where T is the absolute temperature, right? So we have the definition of the Charles law once again redefined, or the modern definition of the Charles law, according to which the pressure remaining constant, the volume of a fixed mass of gas, is directly proportional to its absolute temperature. Perfectly fine. I hope the whole concept should be now very well into your brains. You will not be forgetting anything. This is going to be every bit of it very important for you. So now we will be doing, after the theoretical part of the Charles law, the discussion on the graph related to the Charles law. But before that, I just want to ask you two very simple questions. These questions are actually very simple, but well, they will help us understand the graph better. Okay. So the first question is that at what temperature does the volume of a gas become twice the initial volume V0 at 0 degrees Celsius? So you now know all the equation for the Charles law, that is Vt equal to V0 plus T by 273.15 of V0, right? So what you can do is put this as 2 V0 and find out the value of T. But even if you don't do that, it is going to be very simple for you to understand that what we want Vt is to be equal to 2 V0, right? So V0 plus V0. It is only this thing that we want to be equal to 1, so that we get V0 plus V0. So what should be the temperature? Well, the temperature should be 273.15 degrees Celsius. This you will be getting Vt equal to V0 plus 273.15 over 273.15 of V0. So this is going to cancel. What we will be getting V0 plus V0 equal to 2 V0. So what do we draw a conclusion here from? Well, the conclusion we draw is, first of all, that when we are going to increase the temperature, the volume is going to increase. And from 0 degrees Celsius, if you increase the temperature to 273.15 degrees Celsius, the volume is going to become double. Right? Now let us move on to the opposite part. What are we going to do? Well, we are wanting to decrease the temperature and see what is the effect. So at what temperature does the volume of a gas become zero from the initial volume V naught at 0 degrees Celsius? So you will start decreasing the temperature. For every 1 degree decrease in temperature, the volume is going to decrease by 1 by 273.15 of the initial volume. So putting the values in the equation also, and also by seeing simply the equation, what you will be getting, the value of T is minus 273.15 degrees Celsius. Right? So you can see as well that when we are going to put the value as minus 273.15, this is going to cancel out. V naught minus V naught is going to be left behind. We will be getting the volume to be zero. So what do you understand from this? What we understand is that when we are going to decrease the temperature to minus 273.15 degrees Celsius, what is going to happen? The volume of the gas is going to become zero. Isn't this very interesting? That we are decreasing the temperature, we are just keeping on decreasing, and we are saying the volume is going to become zero. Can the volume of the gas become zero? Where are going to be the atoms and the molecules gone? They cannot go somewhere, right? I hope you can understand this, that the volume of the gas, molecules and the atoms, they may be quite negligible as compared to the volume of the container, but they cannot vanish anywhere. Right? This is something that we will be understanding better when we will be studying the postulates related to the ideal gas, and then we will be understanding that actually we do not have any ideal gas, but they are going to be real gases, because the volume of the gaseous atoms and molecules, they just cannot vanish into the thin air. So what do we have? But theoretically speaking, if we decrease the volume to minus 273.15 degrees Celsius, what we will be getting is the volume of the gas coming up to zero. Perfectly fine, I think. Now this minus 273.15 degrees Celsius is what? You all know that this is 0 Kelvin. Fine. So we can actually define the zero of the Kelvin scale or the absolute temperature scale from this, that it is going to be the lowest temperature on the Kelvin scale where the volume of the gas is going to become zero. I will be putting up the definition onto one of the slides also, but I hope you can understand this. Fine. Now let us move on to the graph of the equation, graph for the Charles law. So here we have a graph for volume versus temperature in degrees Celsius. So what you can see is that we have drawn 4 graphs for volume versus temperature at 4 pressures, right? So we have one graph to be at the same pressure. So the plot of the volume against temperature at constant pressure, this is called as the isobar. So just like we drew the graph for the Boyle's law, it was volume versus pressure, or pressure versus volume at a constant temperature, and we call that graph to be a isotherm at one constant temperature. So similarly over here we have at same constant pressure the plot of volume versus temperature to be called as a isobar. Fine. Now, if you look at this graph, what you have learnt is that the volume is going to increase with increase in temperature. So you can see that as the temperature is increasing, the volume is also increasing, right? And now, one thing more, when you're going to see that if you're going to decrease the temperature, let us see that we are say at 0 degrees Celsius, this is the volume that we have. So we keep on decreasing the temperature, we keep on decreasing the temperature, and this comes up to this level of minus 273 0.15 degrees Celsius to be more precise, which we have written as minus 273 degrees Celsius. So this is 0 Kelvin, and this is the point where the volume of any gas is becoming zero. Fine. So how do you understand this? Well, you may take whatever gas you want. Just let me draw it. Okay, so you may take any gas in a container, right? So supposedly I have gas A in this container. So when I am going to decrease the temperature by 1 degree Celsius, it is going to decrease in this way, so that we had divided into 273 parts, and by the time we reach up to a decrease of minus 273.0 degrees Celsius, the volume is going to become zero. Similarly, if I take a B gas, now this B gas has a lesser volume, but the lesser volume also, it is going to be divided again into this 273 parts, right? So every time when we are going to decrease the temperature by 1 degree Celsius, the volume is going to decrease by 1 by 273 part, and ultimately after the decrease of minus 273 degrees Celsius, this volume is also going to become zero. So all these graphs, you can, I hope, understand now that they will be converging to the same point. So they will all be converging to the same point, that is that they will be reaching up to 0 Kelvin. So these all graphs, they will be combining, joining to each other at 0 Kelvin. And this also you can understand, just let me rub this, that we have the equation for the Charles law to be V equal to K2 into T, right? So when we write this, we know that V is directly proportional to T, but we can write this equation as Y is equal to mx plus C. Right, so C is 0. So this means that there every graph over here, it is going to start from 0 Kelvin. So when we are going to draw a graph of volume versus temperature, and the temperature taken on the Kelvin scale, we will be starting from this point, right? So my line on the volume would have started from this line, and at that point the C is 0. So this means that the line is passing through the origin. So if I have to draw a graph for volume versus temperature on the Kelvin scale, my line on the volume of the y-axis would be starting at this point, and this would be my graph. This is on the temperature in the Celsius scale. So that is why it is not starting from the 0 of the temperature scale, because here the value is going to be 273 Kelvin, right? So I hope this is clear to you. Another thing now which is going to be very important is this M and K2, right? So M gives us the slope of the line, and over here in this equation K2 is giving us the slope of the line. So slope of the line is going to be equal to tan theta. So if the value of theta is going to be more, the value of tan theta is going to be more, value of tan theta is going to be more, the value of K2 is going to be more, right? So what you have now learned is that K2 is inversely proportional to the pressure, right? So if the value of theta is going to be, say, less, right? So this theta over here, if I write this as theta 4, then this would be my theta 3. So if my theta 4 is less than theta 3, this means that tan theta 4 is going to be less than tan theta 3. The value of K2 for this pressure P4 is going to be less, right? So when we are drawing this line, the K2 is coming to be less than this, and therefore the pressure P4 is going to be greater than P3, and P3 will be greater than P2, and P2 will be greater than P1. So if you are asked now a question that which of these is going to be a greater pressure, I hope you can understand that P4 will be greater than P3, P3 will be greater than P2, P2 will be greater than P1, because pressure is inversely related to K2, and K2 is going to be equal to tan theta. Fine, I hope this is clear. This is very important for you to understand. Now we can draw various other graphs also for the Charles law, like we drew for the Boyle's law, but well, I'm not going to discuss them over here. I will be carrying on that discussion onto the next lecture, where we will be taking the problems based on the Charles law. So I will be giving you again a few graphs from which you will be having to choose which one is going to be the correct representation for the Charles law. So you can practice them over there, and and then check with the solutions that will help you understand those graphs better when you're going to solve them yourselves. Now, there have been certain points that I have been discussing with you while we were having our discussion on the previous slides, but they were not written down for you. So I've just written them down also so that you remember them always. Okay. So the absolute zero, while we were talking on the last slide, with the zero of the thermodynamic temperature scale, or the zero of the absolute temperature scale, or the zero of the Kelvin temperature scale, it is going to be that temperature, the lowest temperature where the volume of the gas, this should become zero, but this is only a theoretical possibility. It is never going to happen, and it is never going to happen because a temperature of 0 Kelvin is practically not achievable. The gases, they are going to liquefy just before reaching this temperature, and therefore the Charles law is not going to be applicable. Right? I hope this is clear. Now, another thing that we have been discussing while we were talking about the hot air balloon was that the volume increases with increase in temperature, and when it is going to increase, the density of the gas is going to decrease, right? So because the density decreased, so the balloon, this had less of a density than the surrounding air, it became lighter and it just went up into the air, right? So the volume increases with increase in temperature, the density decreases. So what we can say is that at constant pressure, the density of the gas is going to be inversely proportional to temperature on the absolute scale. Fine. I hope you will remember this very important information. And finally, about the Kelvin scale, what we have learned is that this is going to be that scale of temperature which will be starting from minus 273 degrees Celsius as its zero. Fine. I hope all this thing now with all this information is perfectly fitting into the picture. Everything is crystal clear. So now, before I can wind up the lecture, quickly telling you the applications of the Charles law, which you have actually learned also. The first is that the volume of the gas is going to increase on heating, which is going to reduce the density of the gas, and it is going to be very important for one of the most important application that you have learned, the hot air balloon. So the hot air balloon, they are used in sports and meteorological observations. And why they are used? Because hot air is less dense than cold air. Volume is directly proportional to temperature. On increasing the temperature, the volume is going to increase and the density is going to decrease. So I hope I have written down everything that I have been speaking out, and you will remember all this information. But before ending, just a quick look on to some experimental data for the variation of volume with temperature for a given mass of gas at constant pressure. It is just a quick look at all the data that we have, that we are increasing the temperature on the Kelvin scale. What we are seeing is that the volume is going to increase, and if we take the ratio of volume by temperature on the Kelvin scale, what you will be getting is that V by T is going to come as constant. So this is what is Charles law. So that would be all for the Charles law. I hope we have had a detailed discussion and everything is clear with you people. And if you've liked the lecture, please do click on the like link before leaving. And also, if there are still any doubts left after all this discussion also, do not hesitate. Please do put your doubts on the comment section, email them to us, or join us on the Facebook page of the channel, wherever you like. But please do not keep your doubts to yourself. See you again. Have a nice day. God bless you.